In this video, we're going to see how to compare different data sets to see if there are significant differences between their means. So we have three data sets here. We have data set A, data set B, and data set C. And we have computed the means for these three data sets. They look like they're different, but it may be that these apparent differences are just the result of random error. And we want to see whether or not we can reject the hypothesis that the differences between these come purely from random error. So the proper test for that is the t-test. But we have to do an f-test first. In a previous video, we compared the precisions of the three data sets. And we wanted to know if we could say that the different data sets had significantly different variances. Here's where we did that test. We compared data set A versus data set B, and if you look at the other video, you can see this in a little more detail, but we did an f-test here, which you can easily do just by selecting the two data sets right here, and it gives you the p-value then for the f-test. What's a p-value? The p-value is the chance that you will be wrong if you reject the null hypothesis. In this case, our null hypothesis is that any differences in the variances come purely from random error. And there's an 87% chance we'll be wrong if we reject that null hypothesis, so we couldn't reject it. Essentially what we found, since none of the p-values were 0.05 or less, essentially what we found here is that all of the data sets have essentially equal variances. We cannot say that they have significantly different variances. So that's going to determine how we do the t-test in some ways. There are two ways to do the t-test, a long way and a short way. The short way is to just calculate the p-values for the test. That's the easier way. Let's do that first. I am going to use the t-test function, t-test, in Excel, and it's got 4 arguments. The first one is the first array you want to compare. We're going to compare data sets A and B. And it doesn't matter if I select blank cells or not. It's going to ignore any blank cells that I select. So those are the two arrays those are the two data sets that I want to compare. And now it wants to know how many tails I want on my distribution. We're always going to want 2 tails. So you always put a 2 there. And then it wants to know what kind of t-test I want to do. I do not want to do a paired t-test. I want to do a 2-sample t-test with equal variances. That's option 2. So I'll put a 2 there for that. Now, if the variances were unequal, that is, if I found up here that any of these variances were significantly different, I would choose 3 there instead of 2. All right. Then I close it off. Now, it gives me this number, 0.53563. What does that mean? It means there's about 53.6% chance that if I reject this null hypothesis, I'm going to be wrong. That's a pretty high percentage, so I'm not going to be able to reject the null hypothesis. In other words, I cannot say that there is a significant difference between the mean for data set A and the mean for data set B. I can't conclude that. All right, and I can do this for the other pairs of data sets too. I can use the t-test function to compare sets B and C. And I want 2 tails again, so I put a 2 there. And the type is type 2 because my variances are essentially equal, it looks like. Now here there's an 85% chance I'll be wrong if I reject this null hypothesis. And that means I cannot say that there is a significant difference between the means for set B and set C. I cannot say that. I cannot conclude that. Okay, let's compare set A and set C. I'm going to use the t-test function again. I'm going to select set A and then comma, and I'm going to select set C and then comma. I am going to use two tails, so I'll type a 2 there. And once again, we found that the variances for sets A and set C were essentially equal. So I can just put a 2 there. And there's only a 37% chance that I'll be wrong if I reject the hypothesis that any differences between this number, 3.9, and this number are due to purely random error. But 37% is still a pretty good chance that I'll be wrong if I reject that hypothesis. So I won't reject it. You can only reject the hypothesis when the p-value is 0.05 or less. All right, so that's the easy way to do t-tests and to draw conclusions about whether the means are significantly different or not. There's a longer way to do it and not as good a way, actually, and that is to calculate the pooled standard error. You sometimes have to do this anyway if you want to throw all of the data sets into one pool and give a confidence interval for the entire pooled data set. You'll sometimes have to calculate this pooled standard error here. Let's do it the long way here. We should come to the same conclusions that we came down here, which was that we could not reject the null hypothesis in any case. All right, so the pooled standard deviation, A versus B, I have the equation for this, and this applies when you have equal variances. There is a separate equation for this when you have unequal variances. But we've got equal variances here. So I'm going to type this equation into Excel. It looks like I've got a square root around the whole thing. So I'm going to type it in like that first. Now I'm going to put something inside there. I've got this expression here on top divided by this expression here on the bottom. So let me go ahead and put parentheses around the top expression and parentheses around the bottom expression. Now that helps me match the parentheses if I put them in like that. Finally, I have that whole fraction multiplied by something else in parentheses over here. So I'm going to put a pair of parentheses there for that. Now let's fill in the parentheses. This parentheses are going to encompass this part of the expression. Okay, so I've got parentheses na minus 1 times sa squared. Na minus 1, close the parentheses, times, and here I've got the variance. The SA squared here is the variance of set A, plus NB minus 1, close the parentheses, times the variance for set B. All right, so I have got this part of the expression typed in. Now let's do the denominator, this thing down here. It's going to be NA plus NB minus 2. And now I have this whole first fraction typed in. And now I've got this times the second fraction over here, which is 1 over NA plus 1 over NB. here's NB. And it gives me a pooled standard error of 0.34. Okay. How many degrees of freedom do I have for the t-value I'm about to calculate? This is actually the degrees of freedom here, NA plus NB minus 2. So it's going to be NA, whoops, I have to say equals, NA plus NB minus 2. That's the degrees of freedom I have for this comparison. Now I want to calculate a t-value for this, and the t-value is going to be it's going to be the difference between the means divided by this pooled standard error. And I'm going to strip the sign off of it. So it's going to be absolute value of the difference between these two means. It doesn't matter which one I put first or second, because I'm taking the absolute value of it, divided by my pooled standard error. That's my t-value. So it's the difference between the means divided by the pooled standard error. And we take the sign off of it with the absolute function there. So there's my t-value. Now I need a critical t-value to compare that to. If my t is bigger than this critical value, then I can reject the null hypothesis with 95% confidence. So let's get the critical value. It's going to be t inverse, and then I want the probability 0.05. If it's 95% confidence, the probability I'll put in there is 0.05, 5%. And then I need the degrees of freedom, which we said was 9. Now my t-value is not bigger than the critical t-value, so I cannot reject the null hypothesis with 95% confidence. Now that's the same conclusion that I drew here with the p-value. The p-value was not 0.05 or less, so I could not reject the null hypothesis. And this says again, I cannot reject it with 95% confidence either. Now, I could go and do B versus C and A versus C the same way. It would be the exact same process, and I should come to the same conclusion I came down here. Now, if you just want to do a t-test and you don't need the pooled standard error to build a confidence interval or anything with a pooled data set, then all you have to do is do it the easy way down here with the t-test function. That's a much simpler way to do this than to do it the long way here. The advantage of that too is that it's not any more complicated to do unequal variances than it is to do equal variances. Whereas doing it this longer way is a little more difficult when the variances aren't equal.